We're going to be looking at a couple of things in this section. We're going to be looking at calorimetry, energy transfer, and molar enthalpy. We'll get to that in a little bit. Let's talk about what a calorimeter is. It's simply a device that is used to measure a heat change. So essentially, it's just a well-insulated chamber like a thermos that can hold water, and that water is what's going to absorb the heat change. And there's also a thermometer there to measure the heat change. So there's a couple of examples here. This is your classic styrofoam or coffee cup calorimeter, and then these ones are that's a bomb calorimeter. Those are your big boys right there. So there are two types of calorimeters. I mean, there's only one type, but it's the assumptions that we use that set them apart. Firstly, we've got a simple calorimeter. So with this, we assume that the water is the device that absorbs all the heat of the reaction. We assume the calorimeter absorbs no heat, and we assume no heat is lost to these surroundings. Probably the coffee cup calorimeter you saw on the previous page is probably the closest thing we've got to a simple calorimeter, because the styrofoam is really not going to undergo a heat change. So if you think back to all the questions that you did in the first part of 5.2, those would have been considered in a simple calorimeter. The calorimeter wasn't undergoing heat change. So the complex calorimeter, we assume all parts of the device absorb heat. So if it's made of metal, the metal is going to warm up or cool down. And we assume all parts of the device have the same initial and final temperatures as the water. So we've got this equation that we became familiar with in the earlier section, but we actually need to do it twice because we have water that's undergoing a heat change and probably the device itself. So here's a question. A steel calorimeter with a mass of 322 grams is filled with 225 mils of water. Now we do want to work in grams, but hopefully you remember that 1 mil of water is equal to 1 gram. So technically it's 225 grams. The starting temperature of the device in the water is 10.6 degrees, and we have 1.02 grams of ethanol that gets burned, and our temperature rises dramatically. So we've definitely got an exothermic reaction. So firstly, let's calculate the heat change here. So I just went ahead and took the water numbers. There's our mass of the water, our specific heat capacity of water, and our temperature change. And then I repeated with the mass of the device, the specific heat capacity. So it said it was steel, so a quick little Google search yielded that value. And then the same temperature change. Remember we said the temp change will be the same for the water and the device. Plug your values in, and you get about 30,000 joules or 30.11 kilojoules. Now we have to be careful here because this is an exothermic reaction. And what we've learned, or are currently learning, is that anytime we have an exothermic reaction, our answer is in fact negative. Exothermic reactions have negative values. And this is the case where we just have to rationalize this one. Our answer came out to be positive, but really our system has lost the energy, the surroundings is warmed up, and really we have to focus on the system. So we end up with a negative value there. So next thing we can do is something called the heat of combustion. The key part here is it's in joules per gram. So there is our C for combustion. We're going to see a little bit more about this in a second. And there's our values. Now we're taking the mass of the sample here. And again, I included the negative up here, so this answer gets to be negative as well. So again, it's a fairly large answer. Now, one other thing, we're going to continue on with the idea of enthalpy. What's the enthalpy change here? So our enthalpy change, it's actually, I guess I forgot to put it here, it's in kilojoules per mole. So we're going to have to find the moles. We're going to have to find the moles of ethanol. So I took the liberty of doing that. This may seem familiar back in grade 11. There's your molar mass. Cancel, cancel, and we end up with 0.22 moles. So simply what we're after here is and there's our enthalpy change, and the R stands for the reaction. We're just going to divide those two numbers, and we get our answer in kilojoules per mole. So let's talk more about this enthalpy idea. So every substance undergoing a chemical or physical change contains a certain amount of thermal energy. The total amount of thermal energy is known as enthalpy, or H. So the energy change that occurs in a system during a reaction is called the enthalpy change, or delta H. So this may seem a little odd at first. So what we're talking about here is the enthalpy change of the system, and what we've done is we put the absolute values around the energy of the system. We have to focus on something here. So we're focusing in on the system, and we can always end up with a positive value with the absolutes, but we have to realize that in exothermic reactions, our enthalpy is going to be negative, and when it's endothermic, our answer is going to be positive. Let us guide that. If you can remember this little thing here, then all this other stuff will sort of just kind of fall into place. So what we're going to be doing here is we're actually going to be taking the enthalpy of our products and subtracting off the value of our reactants. So when the products of a reaction have a greater enthalpy than the reactants, delta H will be positive. And this is endothermic. Okay, this is what I was just talking about here. And then the opposite for the exothermic. Exothermic has negative. And so this is, of course, saying that heat is released into the surroundings. Again, you got to look at it from one perspective. Either you're looking at a perspective of the surroundings, or you're looking at it from the perspective of the system. And so we're looking at the system here. And so system in exothermic is losing energy. Okay, it's going into the surroundings. It seems hot. And then the opposite for endothermic. And then here's these values again just written. So when your delta H is greater than 0, it's endo, and when it's less than 0, it's exothermic. So here's just an example from the book. You've got a reaction here. This is an exothermic reaction, so your heat is dropping. So the energy of the system has gone down, where the energy of the surroundings has gone up. So the surroundings would have a plus value and the system would have a negative value. But again, we can only look at it from one perspective, and our choice is going to be from the system's perspective. So let's talk about the molar enthalpy. Notice I put a little X here because X could be a whole bunch of things. So enthalpy changes involve 1 mole of a substance. X stands for the number of enthalpy changes associated with a phase change. And all these phase changes here have different values. So for instance, here's water. It starts as ice and it ends up as steam. So what's happening here on our straight line portions, so from here to here, we would have one particular delta H value. So this would be like your delta H melting. Now you can have a whole bunch of different things here. So this would be the melting one. We get up here, we've got water, so this would be a delta H, and this would be like vaporization. All right, so there's even more. You can even reverse these, right? Because you could say you could have the graph going backwards, and instead you'd have the enthalpy of condensation, or the enthalpy of freezing. So there's a whole bunch of these things. They all kind of sort of play out the same though, but they do have different values. So you start looking these things up on the internet, you're going to find they get different values for water. It's really all depends where the question is taking place. So here's an example, and these are just types of molar enthalpy changes. So we've got the delta R there. So there's solution, combustion, vaporization, formation, neutralization. So there could be a whole bunch of different letters here. So molar enthalpy results from simply dividing the enthalpy change by the number of moles present. So this little equation will be nice to use in a moment. We're going to be looking up values for this and then solving for our delta H of the system. Okay, so in this one we are going to determine the enthalpy change if 100 grams of water vaporizes. So this vaporization term we can actually Google and look up on the internet, and there it is. So what we're after is just the enthalpy change when this happens. That was a delta, by the way. That's not a good looking delta, but that's what we're trying to solve for here. So old school style, we're just finding the moles of water. So you can do that quickly here. We get 5.5. Our grams cancel with our grams there. We're left with moles. So there's our general equation, but what we want to do is we want to rearrange this for the vaporization. So notice I just changed the X here into the vaporization. We're rearranging now at this point. And all we're taking is we're just taking the N from this side and cross multiplying it up, so it's right there. And then we're just putting in our values. So there's our mole term and the 40 kilojoules per mole. The moles will cancel out, so your final answer is going to be in kilojoules. So there you go. So representing molar enthalpy changes. So there's a couple of different ways to do this. So one way is writing an equation. So let's do it for the synthesis of water, and this it's an exothermic process. So we have a 285 kilojoule result there. There's a different way to write this. And because it's exothermic, our delta H is going to be negative. I've tried to establish that already in this lesson. Now you can also do this with a potential energy diagram. I think we saw these earlier. And so what you do if it's exothermic is you write your reactants right there. There's a drop in energy for the system. And there are your products. And once again, you'll notice that this was represented with a negative value. If this were endothermic, we'd switch it around and this value would be positive.